planet under this life-giving sun. Now, let's talk about that very sun, the brilliant ball of fire that rises every morning, warms our skin, grows our food, and makes life on Earth possible. It feels constant, eternal, the unwavering center of our daily lives. But here's a cosmic truth that reshapes our understanding of time itself. Our sun, just like every other star, has a lifespan, and its final chapter will see it transform into a dense, Earth-sized ember called a white dwarf. Yeah, you heard that right. The powerhouse of our solar system won't blaze forever. Billions of years from now, it will undergo a dramatic metamorphosis, leaving behind a shimmering, incredibly dense remnant that will slowly fade into the cosmic darkness. It's not doom and gloom. It's the inevitable, beautiful cycle of stellar life and death, playing out on a timescale so vast it humbles our human experience, yet connects us profoundly to the universe. So, how does a star like our sun live and die? Think of stars as cosmic furnaces, powered by nuclear fusion deep in their cores. For our sun, right now, it's in the prime of its life, a stable phase astronomers call the main sequence. It's been in this phase for about 4.6 billion years, and has roughly another 5 billion years to go. During this time, it's fusing hydrogen atoms, the simplest and most abundant element, into helium atoms in its incredibly hot and dense core. Each second, the sun converts millions of tons of hydrogen into helium through this process, releasing a staggering amount of energy in the form of light and heat. This energy radiates outwards, fighting the immense gravitational pull that's constantly trying to crush the star inward. It's a delicate, stable balance. Gravity pulling in, fusion energy pushing out, that defines the sun's current, life-sustaining state. The energy released is what we experience as sunlight, bathing Earth in warmth and driving our climate and ecosystems. But nothing lasts forever, not even the hydrogen fuel in the sun's core. After about 10 billion years total on the main sequence, that core hydrogen will start running low. The fusion factory begins to sputter. This is when the sun's graceful aging turns into a dramatic midlife crisis. With less fusion energy pushing outward in the core, gravity gains the upper hand, squeezing the core even tighter. This compression makes the core hotter and denser. Meanwhile, the outer layers of the sun, responding to the changes deep inside, will start to expand massively. The sun will balloon outwards, transforming into a red giant star. Picture this, the once familiar sun swelling to engulf the inner planets. Current models suggest its outer atmosphere could easily reach beyond the orbit of Mercury, then Venus, and quite possibly even Earth. Our planet, bathed in the sun's outer layers, would be scorched beyond recognition, its oceans boiled away, its surface melted. The once life-giving star becomes a planet eater. During this red giant phase, the sun will be hundreds of times larger and thousands of times brighter than it is today, dominating the sky as a monstrous ruddy orb. This phase will last for about 1 billion years, a relatively brief, but incredibly violent chapter in the sun's life. What's happening inside during this expansion? While the core was collapsing and heating up under gravity's grip, the intense heat ignites a new kind of fusion in a shell surrounding the core. Hydrogen that wasn't hot enough to fuse before now gets heated sufficiently to start fusing into helium. This shell fusion releases even more energy than before, which is what causes the outer layers to puff out so dramatically. Meanwhile, the core itself, now mostly helium and squeezed relentlessly by gravity, continues to get hotter and denser. Eventually, it reaches a critical temperature, around 100 million degrees Celsius. At this point, the helium atoms themselves start fusing. Helium fusion is a more energetic process, creating carbon and oxygen. This helium flash provides a new burst of energy, but it doesn't stop the red giant expansion. It might even make it more unstable. The sun will pulsate, shedding vast amounts of its outer material into space in powerful stellar winds. Its grip on the outer planets will weaken, and their orbits will drift further out into the cold. The red giant phase, while destructive for the inner solar system, sets the stage for one of the most beautiful spectacles in the cosmos. As the sun nears the end of its life as a giant star, it becomes incredibly unstable. The fusion processes in its core and surrounding shells become erratic. In powerful, convulsive bursts, the sun will eject its entire outer envelope, the vast, distended layers that made it a giant, into space. This ejected material expands outwards, forming a glowing, intricate shell of gas and dust around the dying star. This is a planetary nebula. Don't be fooled by the name. It has nothing to do with planets. Early astronomers using small telescopes thought these glowing shells looked a bit like fuzzy planets, hence the name. A planetary nebula is the dying star's final, magnificent artwork. The intense ultraviolet radiation from the incredibly hot core now exposed will light up this ejected gas, causing it to fluoresce in vibrant colors: reds from hydrogen, greens from oxygen, blues from helium. Famous examples like the Ring Nebula or the Helix Nebula show the breathtaking beauty of these structures. Our sun, though smaller, will create its own unique, ephemeral cosmic bloom visible across interstellar distances. This nebula phase is relatively short-lived, lasting maybe 10,000 to 20,000 years before the gas disperses too thinly into the interstellar medium, enriching it with new elements like carbon, nitrogen, and oxygen, the very elements essential for life. What remains after the nebula dissipates? The fate of the sun's core. With no more fusion possible, it doesn't have enough mass to crush carbon and oxygen further into heavier elements like iron. The nuclear fires go out for good. All that's left is the incredibly hot, incredibly dense core exposed to space. This core, roughly the size of Earth, but containing about half the original mass of the sun, is the white dwarf. Imagine squeezing the mass of the sun into a volume the size of our planet. The density becomes mind-boggling. A single teaspoon of white dwarf material would weigh tons here on Earth, as much as an elephant. This density is possible because the atoms themselves have been crushed. Electrons are stripped from their nuclei and packed together so tightly that they form a state of matter governed by quantum mechanics called electron degeneracy pressure. It's not fusion holding it up anymore. It's the fundamental quantum rule that says electrons refuse to be squeezed into the exact same state. This electron pressure is incredibly strong, but it has a limit. Luckily for our sun, which is a relatively low-mass star, electron degeneracy pressure is sufficient to prevent further collapse. More massive stars face different, more violent fates. The newborn white dwarf is blisteringly hot, perhaps over 100,000 degrees Celsius initially, shining with an intense, brilliant white or blue-white light. But with no internal energy source, it has only one path to cool down. It radiates away the heat left over from its fiery past, slowly fading over billions upon billions of years. It starts white-hot, then yellow, then red, and finally becomes a cold, dark black dwarf, a dense cinder of carbon and oxygen floating in space. This cooling process takes an unimaginably long time, far longer than the current age of the universe, 13.8 billion years. In fact, the universe isn't old enough for even the first white dwarfs ever formed to have cooled to black dwarfs yet. So every white dwarf we see in the sky today is still on its long, slow journey towards darkness. They're the embers of dead stars, gradually fading. What happens to the solar system after the sun becomes a white dwarf? The inner planets, Mercury, Venus, Earth, and likely Mars, are gone, consumed during the red giant phase. The outer planets, Jupiter, Saturn, Uranus, Neptune, and the myriad of moons, asteroids, and comets will survive, though profoundly changed. Their orbits will be much wider due to the sun losing so much mass. Mass governs gravity. The once warmth of the sun will be replaced by the feeble glow of the white dwarf. Jupiter and Saturn will become dark, frozen worlds. Any moons that might have had subsurface oceans will freeze solid. The light from the white dwarf, though initially bright, will be a pale, cold imitation of the warm sunlight they once knew, and it will steadily dim over the eons. The solar system will become a dark, frigid place orbiting a slowly fading jewel. Debris disks might form from asteroids and comets perturbed during the sun's death throes, and some material might even rain down onto the white dwarf's surface over time. The fact that our sun will become a white dwarf isn't just a distant prediction, it's confirmed by observation. We see white dwarfs everywhere in our galaxy. They are the most common stellar corpse. Telescopes like Hubble and the upcoming James Webb Space Telescope have studied them in detail. We see them embedded in planetary nebulae, confirming the ejection process. We see them in binary systems, sometimes pulling material from a companion star. We see their incredibly dense nature confirmed by their small size and high surface gravity. Studying these white dwarfs tells us about the final stages of stellar evolution for the vast majority of stars in the universe. Stars like our Sun. They are cosmic tombstones, bearing witness to the lives and deaths of countless suns. The elements forged in their cores and ejected in their planetary nebulae, carbon, oxygen, nitrogen, are the raw materials from which new stars, planets, and even life itself can form. We are literally made of stardust, recycled from the deaths of previous generations of stars. So, the next time you feel the sun's warmth on your face, remember its incredible cosmic journey. It's a middle-aged star, faithfully fusing hydrogen, providing us with life. But billions of years from now, it will swell into a red giant, engulfing the inner worlds. It will then shed its beautiful, luminous shroud as a planetary nebula, enriching the galaxy. And finally, it will settle down as a white-hot, Earth-sized diamond in the dark, a white dwarf, radiating its stored heat for trillions of years before fading into a cold, silent black dwarf. This transformation isn't an end, but a transition in the grand recycling scheme of the universe. The elements created in the sun's core and released in its death will one day be part of new stars, new planets, and perhaps new life elsewhere. Our sun's destiny as a white dwarf connects us to the vast cycles of cosmic time, reminding us of the impermanence of all things, yet also the incredible legacy of matter and energy that endures. It's a story of stellar life, death, and legacy written across eons, a testament to the power and beauty of the universe we call home. Thanks for contemplating the distant future of our star with me today. Stay curious, stay healthy, and cherish the light of our sun while it shines.